welcome back to our final segment. Now we're looking at the concept of current in terms of, the mathematical equation. How exactly do we solve problems that relate to the concept of, current? But remember, the facts still remain that current is the rate of flow of charge. So we're asking ourselves important questions like, okay, think about what exactly it means when we've got a current of 3 amperes, or when there is an ammeter reading of 3 amperes. Now that we have demonstrated how exactly we measure current using an ammeter by connecting it in series or at a point, so that we get an indication of the amount of charge that passes through that point per second. So the main question here is, what exactly does the magnitude of the ammeter reading tell us about an electric circuit? And then secondly, what if there was double the amount of current registered by the ammeter? So now we've got 3 amperes, all right? And then if we double 3 amperes, what do we have? We've got 6 amperes. Now, what does that tell us about the current strength or the current intensity? Or alternatively, what does it tell us about how much charge passes through a point in 1 second? So if it's 3 amperes, we are saying that there's 3 coulombs of charge, whatever that number of electron is that pass through that point in a second per second. So if we double it to 6 amperes, what does it mean? It means there's 6 coulombs of charge passing through that point per second, right? And then what does the brightness? This is a very important observation that we made in the previous demonstration. What does the brightness of the light bulb suggest about current in a simple circuit? There's something that we realized, that the more current passes through a light bulb, the brighter that light bulb burns, okay? So in other words, it says to us, if there is more charges passing through that point per second, it means the brighter the light burns, because that has also to do with something very, very important, which is the energy conversion that takes place in a simple circuit. So these are some of the thinking points that you have to actually consider, just to guide us for the purpose of our discussion. Now we want to measure the current passing through a simple circuit where we connect a light bulb, okay? Now, if we go back to our simulation, we will get something of this sort, okay? Now, I'll break that circuit just for us to, to actually measure the current, okay? Now, if we close the switch, there will be current, okay? Or charges will flow. That's very important because we are saying charges flow, and the moment there is the rate of flow of charge, there is current. So we don't use the term current flow, okay? We need to try by all means to stay away from that. Now, if we close the switch, the bulb burns. Now, you need to realize something here. The amount of charge that passes through the first ammeter is actually 4 coulombs of charge. Even after the battery, after the light bulb, they're still the same. So then the amount of charge actually remains the same, which takes us to something that we already know, which talks about the amount of charge remaining constant. Okay, what is that about? It has a lot to do with the principle of conservation of charge. Charge, in the amount of charge, as long as it's a closed system, it will remain constant. So as a result, charge is never lost, okay? Even the energy that is transferred by the battery to these charges remains constant, because we're still emphasizing that, in an electric circuit, there is a lot of energy conversion that takes place. We discussed that earlier to say chemical potential energy from the battery or the cell, whatever the case may be, is transferred to these charges. And then the moment these charges are given energy to move, which we talk about in terms of voltage, energy per coulomb of charge, then we've got electrical energy. What if now this electrical energy reaches the light bulb? What does the light bulb do? There's further energy transformation on the light bulb in terms of electrical energy to light energy. Okay, so the principle of conservation of charge says to us that the amount of charge remains constant. So even if we've got 4 coulombs of charge passing through the first ammeter, and then we also have the same amount of charge passing through the second ammeter. So is there any charges lost in this circuit? Definitely not. So the amount of charge remains constant because we want to think of a circuit as a closed system of some sort, because we're already familiar with the principle of conservation of charge. So the amount of charge passing through second ammeter is equal to that which passes through the first ammeter. So in other words, we can also tell from this simple circuit that there's the same number of charges pass through the light bulb, which is also a very important realization that we have to arrive at, okay? Right, so that's how we measure current in a simple circuit across, through a light bulb, okay? Now, the strength of current in a circuit is determined by the resistance of the circuit. Okay, the term resistance is starting to come up, you know, we're starting to use it once too often than others. So the word resistance, we would understand it in the concept that it has to do with the other devices that are connected in the circuit outside the battery for now. So what are we saying? We are saying that, you know, a light bulb offers some resistance. You know, if a light bulb has got, you know, a certain amount of resistance to the flow of charge or to that current, then it has to do with the amount of energy that it converts from electrical to light energy, because that's what a resistor does, okay? So these are components in a circuit. An example is a light bulb. So we can say, e.g., light bulb, okay? So a light bulb will convert electrical energy to light, heat and light. A speaker will convert, electrical energy to sound energy. So still, we're still maintaining that indeed energy cannot be created or destroyed. So energy is never lost. By all means, energy is transferred from, actually is transformed from one form to the other. So we can talk of a speaker as well as an example, a heater, you know. But in real life, we talk of, you know, television sets, your fridges, your microwave oven, you know, heating and, you know, devices that we use or appliances that we use at our homes, okay? So the strength of current is determined by the resistance. This will lead us to even more, you know, understanding as we go further in our study of circuits, okay? Now, the battery stores a limited amount of energy, okay, for moving charges. So the battery does not release charge. Once again, what it does, it transfers that chemical potential energy to the charges so that the charges can move, so that it becomes electrical energy. We need to get that out of the way. So the charges are not from the battery. The battery is the primary source of energy, which is transferred to the charges, okay? Very, very important, okay? So a battery may be designed to deliver, let's say, a current of 1 ampere for 48 hours, right? So we are going back to the point that the amount of current will also be determined by the resistance of the components that are connected in a circuit. So say, for argument's sake, we've got a simple battery that delivers a current of 1 ampere for a period of 48 hours before we consider the battery to be flat. So the moment the battery is flat, what are we saying? In other words, we are saying that there is no more chemical potential energy to be transferred or to the charges so that they can be electrical energy. That's what it simply means. Now, if a circuit draws a stronger current, we already know something about current intensity. So 2 amperes is double 1 ampere. So it means if we connect it to an appliance that has got greater resistance, which draws a current of 2 amperes, that battery will only do the same job, but for half the time, okay, before we consider it to be flat. So instead of it lasting for 48 hours, because it was designed to supply 1 ampere of current for 48 hours. So in half the time, the battery will be flat. Half the time is like, what, a day, which is equivalent to 24 hours, okay? So this has to do with the real life application of current, okay? Right, now the direction of current in a circuit, very, very important, okay? Electrons are the charges that, whenever we talk of charge in a circuit, we're talking of electrons by convention. We'll explain what that simply means, okay? So electrons are the ones that actually move through the circuit. We'll demonstrate that using a simulation once more, okay? Okay, this is what we have, okay? It's a closed circuit, okay? If the circuit is complete, let's show the charge is moving. There we go. So there's 4 amperes, meaning there is 4 coulombs of charge passing through every point for every second. So this is the direction of flow of what? Of electrons, okay? But we have got what is called the conventional current flow, which is what is standard. So we understand the flow of current with respect to conventional flow. Let's show the conventional flow. So the conventional flow is from positive to negative. This is what it is. So these arrows, they show the conventional flow of current. And in our discussion from now going forward, we always talk about current moving from positive terminal of the battery to the negative. Even through the ammeter, it will be from the positive to the negative terminal. So that's about the conventional flow of current. So each time we talk of conventional, we talk about the standard, internationally agreed way in which we describe the flow of current in all circuits that we set up. Okay, let's go back to our simulation. So by convention, the direction of current is taken to be from positive terminal to the negative terminal, as we have demonstrated that. Right. Okay, so this is what we meant in as far as the conventional current. So that's our positive to negative. So that's our positive terminal to negative terminal. All right. Okay, questions now. Let's consider a simple circuit once again. We have set up a circuit like this, but using the real, devices. Now we can transform that to symbolic representation. We'll get something like this for an open, circuit. Here is a circuit. There are 2 cells that are connected in series. Okay, the switch is open. Okay, there are conducting wires. Then there are 2 ammeters connected at different points, and then there is a light bulb. Okay, so for us to interpret this, we need to understand the meaning of each of these symbols. Okay, now let's think about the following questions. What is the reading on the ammeter? Once the question says what, take note of that language, pay careful attention to it. The moment the question says what, it's either we know or we don't. We don't need to go via a way of calculations for us to arrive at the correct answer. So what, and it tests your knowledge, your remembering. Okay, now this is typically an open circuit, it's a broken circuit rather, because the switch is open. Are there any charges flowing? If not, what is the current? So that's the thinking that we want to apply. So if the case is that it's like this, we can go back to that simulation quickly, right? Let me take out the convention, right? Let's break the circuit by opening the switch. What is the corresponding reading on current? 0. You can even show the charges. Is there any flow of charge there? Definitely not. Okay, there is no flow of charge there. Okay. Okay. So because the charges are stationary, they are static. So hence there is 0 current because there is no flow of current. Okay. So what does this tell us? That once the circuit is broken, it simply means that there is 0 current. Okay. The current reading will be 0 amperes. Okay. Ammeter reading rather. Okay. Right. Now we close the switch. Okay. The moment we close the switch, then there will be a reading on the ammeter. Okay. But now let's also recall that this is the positive terminal and that's the negative. While again on the ammeter, that's the positive end connected to the negative end. Similarly, this is what happens with the light bulb and as well as the what? As the ammeter, because we know that by convention the current flows from the current is from positive to negative, or charges move from positive to negative. So that's convention. Okay. So that we're talking about conventional flow. Okay, take note of that. So the assumption is always that we talk of the conventional. Right. Now, show the direction of current, indicate the positive and the negative terminal. So we would refer back to the source, which is the battery. That's our positive, that's our negative. So that's the direction of conventional flow. So on the ammeter, that's what we have. We have already demonstrated that from the positive to the negative of the battery. Okay, right. So that's straightforward. Now questions that involve, calculations. We are told that 48 coulombs of charge flows through a battery in 2.5 minutes, right? Take note of that time, all right? And we talk of a unit time. Does that suggest something? Yes, there are necessary conversions that have to be carried out in case we want to do some calculations of some sort, okay? It says here, what amount of charge passes through the light bulb in this time? Okay, what do we know? What do we know? We want the amount of charge here. What do we know? We know that current is equals to charge over time, okay? So what are we given here? We are given the amount of charge, okay, and the time. Now we want to calculate the ammeter reading, right? So the ammeter reading is the current. It will give us the indication of current, okay? How much charge is that? 48 coulombs, right? Divided by how much time is 2.5 minutes, okay? Remember, the SI unit of time is the second. So this will be 2.5 or 2.5 multiplied by 60. Why? Because for every minute there are 60 seconds, okay? So our current, if we quickly go to our calculator, okay, what does that give us? We have, let's clear that. The calculation is 48 coulombs into 2.5, okay, multiplied by 60, okay. So what does that give us? It gives us 8/25 as a decimal fraction, 0.32, okay. So the 0.32 is actually the ammeter reading, which is an indication of current strength, okay, 0.32 amperes, right? So be mindful of the fact that whenever you do calculations, make sure that the final value that you are calculating carries the correct unit. We are given the charge in coulombs. We managed to do the necessary conversion from 2.5 minutes to seconds, okay? And then whatever we're looking for in this case, which is the ammeter reading, which is an indication of current intensity or strength of current, or simply put, the amount of current that passes through a point, you know, then we managed to get to that, okay? Then if we can go back, the amount of charge that passes through the light bulb in this time is exactly the 48 coulombs. That's the amount of charge, okay? Right. And then in summary, we understand that current is the rate of flow of charge. This is an all or nothing type of a definition. And then an ammeter is a device, that's an instrument. Current is a quantity, all right? Let's make sure that we understand that. And then ammeter is a device that is used to measure this quantity that we call current. Okay, it is always connected in series or at a point. Okay, the thinking about that was that it actually, we want to establish the amount of charge that passes through a point per unit time. And then we say that, you know, an ampere of current is actually equals to 1 coulomb of charge passing through a point per second. So when we had an ammeter reading of 3 amperes, equivalently what we are saying there's 3 coulombs of charge that pass through a point for every second. So this is the long and short of, you know, what it exactly means when we talk about current. So in as far as the big ideas that have got to do with electricity, what do we know now? We know a lot about current, how to measure current. We can also, by now, measure voltage, you know, either of the battery, okay, which is in terms of the EMF and the potential, the terminal potential difference. But our focus today was on understanding the concept of current, right? So that's as far as, you know, exploring current is concerned. You know, some of the things that are also very important and worth mentioning is that in the calculations that you carry out involving the equation I is equals to Q over delta T, make sure that you copy the formula as it is given. You know, even if we were looking for charge, you'll write the formula as it is given in the data sheet. I is equals to Q over delta T. do the necessary substitution, but be mindful of the fact that there may be cases where you have to necessarily conduct some, conversions to SI unit, because everything is about SI units. And then what follows after that is obviously the maths, okay? Now, that's the time that we have for today in as far as exploring current. Hopefully it made a lot of sense to you. From myself, it's cheers and power.